So this will be the second part about smoothness, etalness, and unramified scheme. And so here we will be concerned about how these general modalities and lifting property are presented work in the case of schemes. And so first, I will give an overview about tangent spaces and first order neighborhood. So first, the definition. So let's write D1 the spectrum of Rx quotiented by x squared. So as I explained last time, this space can be seen as a point 0 together with one tangent vector. And so using this intuition, we say that a tangent vector to x, the type at a small x in x, is a function from D1 to x, such that the function applied to 0 is equal to x. So, which is a very reasonable definition. And so from this you can compute. I mean, you know that, for example, you know that tangent space are functorial in the way you want, because you just need, if you have a map from x to y, you just compose phi with the map from x to y, giving you the map on tangent space. And so, okay, so now we will give another definition. So let x be a type. So we define a relation which are like this, with, which should be understood as saying that x and y are infinitesimally closed to the first order. And so the way we will define this is that we ask that there exists y finitely generated ideal, such that y squared is equal to 0, and y equals 0 implies x equals y. So one particular case is assuming x equals y is a closed proposition, so is of the form that a finitely generated ideal cancels, then them being closed, infinitesimally close to the first order just mean that the square of the ideal is 0. But so we give this definition so that it works in any type. And so then from this notation, for x in x, we define the first order neighborhood of x as the set of y in x, such that x is infinitesimally close to 1. And so, so when x is a scheme, we expect some relation to exist between the first order neighborhood of a point and the tangent space at this point. And so I will now explain this relation. So first, the definition. let M be a finitely presented R module. We define dm as the spectrum of R plus M, and so we need to make this into an algebra. And basically we say that the one here is the unit of the algebra, and that the product of two elements in M is 0. And so you extend this by linearity, and this indeed gives a scheme because we assume the module to be finitely presented. And so here the picture you should have is that you have a point, and then it has some tangent vector which are disembodied. And precisely what you get is that the tangent space at 0 of dm is equal to the dual of M. So we need to take a dual just to have the right variance. So yeah, so for example, what I denoted D1 before is actually D of the R module R. So of the line. And so now a lemma which gives us this relation between first order neighborhood and tangent space. So let X be a scheme and assume a point. Then we have that the first order neighborhood of X is equivalent to D of the tangent space at X, and we need to take a dual as well for variance reasons. And so what it means is that the first order neighborhood of a point X in a scheme is actually the point with tangent vector corresponding to the tangent space of the scheme at this point. So you know, if you have a scheme like this and a point here, the first order neighborhood of this point is actually just this point and a tangent vector for anything in the tangent space here. So yes, so this will be helpful. So
okay, maybe one should also recall that it's not only because of reasons of co or contravariance that we have to switch between M and the dual or the tangent to the dual, but because they are actually living in kind of different category.
Yes.
I mean, one are the finitely presented and the other one are the finitely
co-presented, I would say.
I don't know, yeah.
So yeah, one remark is that the tangent space of a scheme is not finitely presented in general, but it is finitely co-presented because if you have a scheme X, you can merely find that it is the fiber of a map from AM to AM over 0. And so if you go to the tangent space, this translates by saying that you have a linear map here, the derivative, and the tangent space of X is the kernel of this map, so it's finitely co-presented, but not always finitely presented indeed.
Yeah, I mean, in some sense, the naming is bad. That we use, I mean, classically we use space all the time. We talk about the cotangent space and the tangent space, but this is a very different kind of space. The tangent space is something geometric, which translates here in our language into something which is finally co-represented. And the cotangent space and everything else we use as building blocks for taking the spectrum is of an algebraic nature, and this is finally presented. So it's bad that we use the word space all the time. So maybe we can use this. I mean, we can use SAG to decide
how the
space.
cotangent space should be called then.
Cotangent module. Just the first.
Could be so.
Yeah. Fair enough.
I mean, module and vector space are kind of interchangeable, right? Or should this be the distinction? I mean, should I say vector space when I mean an R module that is represented?
Yeah, the vector space is a scheme that happens to have the structure of an R. So that happens to have an R linear structure. This is.
So a vector space object in the category of schemes.
Yes. Okay, sorry for this.
Yeah. No problem. So now let's go. Let X be an affine scheme. Then the following are equivalent. And so first, X is formally unramified. Second condition, X has decidable equality. And third condition, for all X in X, the tangent space of X at X is equal to 0. So let's prove this. So first we prove that X is formally, so first we prove that 1 implies 2. So assume X and Y in X a formally unramified scheme. Then X equals Y is closed. So this we see before. Yes, so if we have that not X equals Y, implies X equals Y, then X equals Y is decidable. Okay.
Too long ago yesterday. So did we see that the diagonal is closed?
Yes, so to see that the diagonal is closed with an affine scheme.
Yeah.
Yeah.
Okay, yeah, this was, I thought it had something to do with
Okay, so now we can assume not X equals Y, but then this means that X equals Y is a closed dense proposition. So we know that any such filler has a unique lifting. And so actually we have two lifting X and Y. Because assuming, so here we have to choose a map. So for example, we send everything to X. Then X and Y are both filling because assuming X equals Y, X equals Y. And so then we have X equals Y. So this gives that 1 implies 2.
So after we assume not X equals Y, we know that the proposition X equals Y is a dense closed proposition.
Yes.
Yeah. Okay.
Yes.
And then we can use the foreground in fact. Okay.
So now let's show that 2 implies 3. So we need to show that decidable equality implies. So we assume x in x. Then n1, the first order neighborhood of x is equal to the singleton with only x. Because if we have an ideal, so since if y is a finitely generated ideal such that y square is equal to 0 and y equals 0 implies x equals y, then we have not x equals y, because y square equals 0 imply that we have not y equals 0. And then we have x equals y because identity type are decidable. Okay, and the third part.
So you could also argue that if you have point x and you have decidable quality, then the scheme x is the single point x plus the rest, disjoint union, and then I take the tension space of the one point of the disjoint union, and intuitively, all the other stuff is far away. So of course, my tension space is trivial. Yes. So that's the intuition. Okay.
Yeah. That would work, and that would. Oh, yeah. Yeah. And so finally, if we assume that. So yeah. By the way, since we have this property here, we know that the first order neighborhood of x being a point is the same as the tangent space being 0 by using the correspondence here, which I didn't say explicitly. And so no, we want to go from 3 to 1. And so, okay, assume epsilon inner is such that epsilon square is equal to 0. We assume a triangle like this with two different fillings x and y. Then epsilon equals 0 implies x equals y. So x belongs to the first order neighborhood of y. And so since we assume that the tangent space is 0, we know that the first order neighborhood is a singleton. And so we get x equals y, meaning that there is indeed a unique lift to any such triangle. And so that concludes the equivalence. I don't know if there's a question in this.
How exactly do you use the tension spaces trivial?
So, since the tangent space is trivial, I know that n1 of y is a singleton. And so then when x is in this singleton, x equals y. So, yeah.
So you only use the tension space in this proposition in the form of the first order neighborhood, right?
Yes. Yes, because it's more convenient to work with in such a context. Erase a bit.
Can someone just remind me under which circumstances in SAG the double dual of a module is the same as the original module?
In this circumstance.
When a module is finitely presented or finitely co-presented, this will work. But in general, I don't know.
Oh, okay, but that's...
No, but here we can just switch back and forth.
Yeah. Since the tangent space is finitely co-presented, so you can switch back and forth freely.
Sorry,
Yes.
I have an alternative proof for one.
Yes.
The truth, because we saw that yesterday. In a formally unramified type, the equality types are formally étale,
Yes.
and any proposition is formally unramified. So, the equality type of a scheme, which is a set, is formally smooth, and formally smooth types are decidable, right? They're formally smooth, closed propositions are decidable.
Yeah, indeed. Indeed.
this is
So I
the same.
proved twice the same thing.
Yeah.
Indeed. Thank you. Thank you for the remark. Yes, and so there is a version for any scheme which I will not prove, but here you just need to replace decidable equality by open equality. And you can deduce from the other using an open cover. So let's go with the corollary. So the map.
What were your what was your assumption now on the schemes? Now you said you can prove it for any scheme, but what was the assumption here? Fine.
Yeah. So when the scheme is affine, you have decidable identity. When you have any scheme, it's open identity. So let's say you have a map between schemes. Then F is formally unramified if and only if for all x in X, the differential for all x in X, yeah, the differential at X is injective. Okay, and so the proof here is not really complicated. So we know that a map is formally unramified if and only if all its fibers are formally unramified. But then we just need to see that for x in X such that f of x is equal to y, the tangent space at x of the fiber of f over y is equal to the kernel of this map. Yeah, well, this map goes to the tangent space at f of x, and I use this assumption to go to y. And so from this, you know that those maps are injective if and only if all the fiber this tangent space are zero, and they are zero if and only if the fiber are unramified. Okay, so now we would like a similar proposition for smoothness. And here we will not get something which holds for all scheme, but we will need to assume something more.
There's a way we can just call it TF. I mean, the relative tangent space or tangent space of the map F.
You mean instead of DF? Writing this?
No, instead of saying that DF is injective, we just say that TF is 0.
Yeah.
And then we have the same. So TF is the function that assigns to an x in X the tangent space of the fiber at that point.
And then we just take all these together. And then we have the same.
Yeah, so both proposition looks more similar this way. Okay, so assume f from x to y, x, y are schemes, and x is formally smooth. Should not forget this. Then the following are equivalent. F is formally smooth. For all x in X, the map is surjective. So this corresponds to what are called submersion in differential geometry. So a map between manifolds whose differential are surjective at all points has fiber which are manifolds as well, and this is a reflection of this in our context. So
I have one question.
yes.
Also, now you say the scheme is formally smooth. But
Yes.
I mean, classically, I mean, formally smooth. A difference between formally smooth and smooth. I mean, isn't it just some finitely generated finite type restriction? So maybe we should call them smooth.
Yeah, that's yes. Okay.
Yeah.
I think I agree, but we should not do it just at this.
yeah, that's right. I mean.
But yes, I agree, and actually that's what we do in the notes. Yeah, I was just careless here. So yes, so first assume F formally smooth. So in this case, it's very easy to show surjectivity because actually we look at this map. So this is a closed dense embeddings because this is an infinitesimal extension of 1. And then actually showing that any square of this form has a filling is precisely showing that df of x is surjective at all points. So if we unpack what tangent vectors mean using D1.
Sorry, with df you don't mean the d you introduced before?
I mean D1 here.
Ah, it's 1. Oh,
Yeah.
Oh sorry. Okay. No sense.
Yes, and so for the converse, so conversely, we assume that df of x is surjective for all points. Then we take, say, epsilon in R such that epsilon square is equal to 0. We assume a square like this, and we want to show that there merely exists a filler. And so first, since x is smooth, formally smooth, I start over. Since x is formally smooth, we know that there exists an x in x such that, so let's call this one y, this one phi. So there exists an x in x such that for all proof of epsilon equals 0, phi of p is equal to x. So here I just choose the formally smooth hypothesis. But then actually call this f. Then we have that epsilon equals 0 implies that f of x is equal to y. So why? Because this square commute, f of x is equal to f of phi of any point here. And so then y belong to the first order neighborhood of f of x. And so we can redraw the diagram. Here we go to n1 of x. This embeds in x. Here we go to n1 of f of x. We have a map here. Okay, and so here I will not prove this completely, but since this map here actually is equivalent to the induced map here. So here we have an equivalence between these two maps, and we know that the map from Tx of, this is an x, from Tx of x to Tfx of y is surjective. We can actually conclude that this has a pointed section. So this I will not do the proof, but I can prove this. So this gives us a pointed section here. And actually then by composing y with this pointed section and this inclusion, we find a lift in the square. So, okay. So as a corollary, we get that if we have that a map from a formally smooth scheme to any scheme is étal, if and only if for all points in the basis the differential is an isomorphism. So maybe I write it down. From x to y, xy schemes, x smooth, so in this situation where x is smooth, f is formally étal if and only if for all points its differential is an isomorphism. And so here again, this agree with the intuition we have from differential geometry and the idea of being an isomorphism in a local sense. What does it mean? Well, when we have smoothness hypothesis, it just means being an isomorphism on tangent space.
I mean, it's clear that you in your proposition before that you need for one direction that x is smooth.
Yes.
Because what can happen is, I mean, even if the differential is surjective, the rank, the kernel can have different rank. So I mean, so counter example would be like something like you take the coordinate cross.
Yes.
And project it down to one coordinate line, and this has surjective differential?
No, I don't think so, because, I mean, at 0 it certainly has, away from 0 it certainly has, but at the neighborhood...
Surjective differential at every point upstairs is the question, right? Or,
Yeah.
And I see points upstairs where I only have vertical tangent vectors.
Okay, yeah, so maybe this was...
Take a point on the y-axis.
Huh?
If you take a point on the y-axis,
Yeah.
then the tangent...
Right, okay,
the
this was
differential is the zero.
not a good counter example. So, okay, well, yeah, then, Okay, another. Okay, so but you can take the double line then. This would be a counter example.
So to what extent?
Smooth?
Counter example?
No, it's not.
Yeah, it's an example why you need the smooth.
Yeah.
Ah,
Okay, yeah, but I hope that it would be enough to detect where the kernel jumps. Yeah, but this is
So for
and
the,
so my hope was that here maybe we do not need smoothness for X, because I mean here we have isomorphism, so the kernel is trivial.
we still need, so we do need smoothness for X, because if you take any proposition and set it into 1, it always obeys this. But
Yeah,
it's not
because
always formally done. So that's,
Okay.
that's too bad, but that's,
Yeah,
that's an actual counterexample. It's not my fault. But yeah, that's a bit annoying. That you quantifying over the base when it's not formally smooth is kind of always a bad idea because of proposition. So yes, okay. So now let's talk about smooth schemes. So here I will prove that smooth schemes have finite free tangent space. So I will first give a sketch of the global proof and then we go into details. So first we will show that for X a smooth scheme and X in X, we have that the tangent space is formally smooth. So here we could even say smooth, because since this is co-presented, this is a scheme. And then we will prove that formally smooth finitely co-presented modules are finite free. So this will be our strategy.
Is in the notes?
Yes. I think so. Okay, so how will we proceed? So, okay, lemma.
7.6 smooth schemes have 3 tangent spaces in differential geometry.
Formally smooth. So I even proof. Let's go. So of course we can define the total tangent bundle, which are simply mapped from D1 to X without assumption on X. And so what we want to show is that the map from this to this is formally smooth. We actually know that this is a scheme. And so the first step is to show that this is formally smooth. And so this holds because D1 has choice. So this, I mentioned that when a type has choice, then the product indexed by this type preserves smoothness, and here we use this. So to see that D1 has choice, so you know that it has Zariski local choice, so you know that for any surjective map to it, it has Zariski locally a section. But actually, since you have a Zariski cover, 0 has to belong to 1 of the open. And actually, then the open is the whole space, because it's infinitesimal. So any open containing 0 has to contain the other. Okay, and now step 2. We need to prove that the map, so we need to prove that the differentials are surjective. And so what this means is that we need to prove for all x and v in the tangent space of x, which R equal is equivalent to an x in x and something, a tangent vector here. So for all elements in this type, we need that the map, so let's call this P, we need that deep P going from tangent space here of T of x to the tangent space is surjective. So, okay, we assume, let's say, W here. And so now we want to express what is an antecedent over here. So to do this, we unfold the definition of tangent space. So okay, I'll do it properly. So for example, this is equivalent to the map from D1, the type of map from D1 cross D1 to X. So, so such that, so let's call this one phi, such that for all T in D1, you have phi of 0 and T equal to V of T. So here, what is a tangent space here? It's a map from D1 to x to the power D1, which send the base point to V. So that's what it means. And then what it means for this map to be sent here. So what does it mean for the derivative of P of phi to be equal to W with this equivalence? It's actually equivalent to ask that for all T in D1, phi of T of 0 is equal to W of T. So here again, we just compute the differential. And so, okay, what situation are we in at this point? what happens is that, so we want to find a map from D1 times D1 to X, which obeys this property. But what we actually have is a map from D2 to X. So D2 is equal to D of R2, which is actually the spectrum of Rxy quotiented by x square, xy, and y square. And so here you have a map phi such that phi of t of 0 is equal to which one do we want? W of t and phi 0 of t is equal to v of t. There is actually a unique such map, which actually is the sum of the two tangent vector. So this I will not prove, but that's one way to actually define the sum, to prove that there exists a unique map. So sorry, not the sum, but what I mean is that the sum of two vectors is defined as phi of tt for a phi from D2 to X obeying this requirement, and we can find a unique such phi, and that's one way to define the sum. But so that's not exactly what we want, because we want a map from D1 times D1 to X obeying this requirement. But actually, this is a closed dense embedding. So we merely find a lift here because X is formally smooth, and that's an antecedent. So now we need to prove that finitely co-presented module that is formally smooth is finite free. So,
is it also, it's probably true that a group scheme is smooth, right?
What do you mean?
Like this usual V group argument that you have translation.
I think you need characteristics.
Ah, okay. I was just wondering, because the intelligent spaces are group schemes, and then you would just take the additive group of the module. Yeah. So we have 0.
I'm not sure it's related, both result and I don't see how, at least. Yeah. Okay, let's prove this. And so first claim we make is that if we have a linear map, say M from Rm to Rn, linear with formally smooth kernel, then M equals 0 is decidable. It's okay. So to prove this claim, so as M equals 0 is a closed proposition, we want to prove that it is decidable, so it's enough to prove that if it not holds, then it holds. And so here, if it not holds, we know that it is closed dense. So we can define the map from M equals 0 to Rm. So, okay, I need 4 legs in Rm. I can define the constant map here, which sends, sorry, not Rm, the kernel of M. So for all x in Rm, I have the constant map sending any proof that M is equal to 0 to the kernel of M, which has just value x, because if M equals 0, then the kernel is the whole space. So from this, I merely get a lift here. So what this means is that for all x in Rm, there exists, let's call this one x tilde, in the kernel of M, such that, so we have that M equals 0 implies that x tilde is equal to x. But so in particular, since we have not M equal 0, this means that we have not x equals x tilde.
What's the difference between the kernel and M equals 0?
Sorry?
What is the kernel actually? Is it not M equals 0?
M equals 0 is just a proposition.
So this is where here.
The kernel of M is a subset of.
Yeah, so M equals 0, it's the morphism M is equal to 0. You see disclosed by seeing M as a matrix, and then you ask for all the coefficients to be 0. Does this clarify? Okay, and so then it means that for all points, you have a point which is infinitesimally close that M send to 0. And so you take a basis of Rm. You get for each point in the basis an infinitesimally closed point that M send to 0. But something infinitesimally close to a basis is still a basis. For example, because being a basis is defined by some determinant being different of 0, and this is preserved by infinitesimal variation. And so then M is 0 on a basis, so M equal to 0. And that's what we wanted to prove. So now we have this claim, and so here it's not too complicated from here. So now we go back to proving that any finitely co-presented module that is formally smooth is finite free. So let's call it P rather. So let us assume that we have such a short exact sequence presenting P as finitely co-presented with P formally smooth. So here we proceed by induction on M. And so first we decide, so by the claim we can decide whether M is equal to 0 or not. So if M is equal to 0, then P is equal to Rm, and we are good, since we want to prove that P is finite free. If M is different of 0, we know that this means that one of the coefficients of M is different of 0. And so then up to base change, M is equivalent to a matrix of the form to a matrix of this form. So we take the invertible coefficient, we rearrange the column and cancel everything. So very down-to-earth linear algebra. And then the kernel of M tilde is equal to the kernel of M, and we conclude inductively because M tilde goes from Rm minus 1 to something. And we conclude by induction. Okay, and so okay, so this result is good. So it tells us if something is smooth, it has finite free tangent space, which is something we expect. And so another result, which I will not have the time to prove, but I want to write down anyway. So let's say proposition. Let X be a scheme. Then X, okay. X is smooth if and only if there exists, okay, yes. Since we have shown that the tangent space of smooth scheme is finite free, it means that we have a well-defined dimension of a smooth scheme at any point, which is the dimension of the vector space. And so here let us that it is of dimension k for a fixed k.
You don't want to say n?
Sorry?
You don't want to say n? Oh, yeah, it's fine, okay. K is also the external base ring used in the model, but that's quite far away from here, so
fair enough.
I don't care.
Let's say n, and so okay, we have that X is smooth if and only if we have a span of this form, where here this is a Zariski cover, and here this is formally étal. And okay, so first, how to interpret this result? So this result is strengthening on the one about tangent space, in the sense that it tells us that not only the tangent space of X are finite free, but even that X étal locally, in some sense, is the same as AN. So this includes that infinite order neighborhood of X are the same as the one in AN, and it's even a bit stronger than this. And the way to prove it is to find actually an explicit form so to prove that any smooth scheme is Zariski locally of an explicit form with some definition on the Jacobian of the polynomials, which I will not get into detail here. And yes, I think I will stop here. Thank you. So, do you have questions? Maybe you just want to eat.
I find this argument about reducing the matrix quite funny. I mean, basically you're really working classically, right? You decide if the matrix is zero, and if not, then you find an entry that is invertible and so on.
Yeah. Yeah, and that gives, I think that's, it's an interesting way to see smoothness, right? That it allows you to decide if some stuff are equal to zero or not, some element of the base ring are equal to zero or not in some nice situation.
Yeah, right, because we use that the kernel of the matrix is smooth to make it work, right?
Yeah. Yeah, that's, and another proof was fairly similar, where you you have something smooth, you want to decide if something is equal to 0, well, you assume it is not equal to 0, then you have a closed dance, you send it in the smooth in some way, and then by completing, you get what you want.
Can we make this some meta theorem? I mean, we try to, so we prove something, or we prove not of something, and then of a form where it's, at the end we land into something smooth, and then we have a way to get out of our not monad.
Here, one thing, so I don't see such a meta theorem. One thing which makes the situation a bit uncomfortable is that being smooth is not a modality. So I would rather look for one with formal etalness, which here seems it seems reasonable to expect something in the line that what Hugo explains. So if you use
but this is on the other side. So I mean, this not. I mean, adding not in front of our theorems, this or our assumptions or whatever. This is I mean, this is the modality.
Yes.
So and smoothness, I mean, to me, looks like comes there from a different angle, because this helps us to get out of this small not.
Yeah. Yeah, and that's. I mean, I think it's a very good question to try to understand formal smoothness in a way a bit more principled, perhaps by its relation to the not modality. I think a remark concerning the not thing. So for a closed proposition, not the proposition is actually the formally étal replacement of the proposition. And so when trying to generalize this more to other types than closed proposition, I would guess using the formal étal replacement rather than the not is better.
Mm-hmm. Yeah, okay. Mm-hmm.
Yeah, might depend on what you want to do.
So can you formulate the smoothness property using not closed dense, but formally étal? Maps?
So it would be rather formally connected map.
Yeah, something like this, yeah.
Not all of them, Not all of them, but maybe formally, say a type is formally smooth is for all, think of this form where P is étal connected. There merely exists a lift. This
closed and étal connected.
So I mean the actual definition is closed and étal connected, but maybe we can use any étal connected type. This at least I don't have a counterexample.
Mm-hmm. Sorry, what is the statement here?
So the statement is not really a statement, but rather I define formal smoothness using closed proposition. Maybe you can define it using any type that is étal connected instead. And so do you get equivalent definitions? I don't know. And if you don't get equivalent definition, which one is better? I don't know. Because in scheme, both will very probably be equivalent anyway. So I'm not sure how to answer which one is better.
So you think for X a scheme It is equivalent. For P,
Well,
any
yes, so yes.
connected type.
Proposition.
Did you mean P is a proposition or any connected type?
Any étal connected type.
Crazy, I have no idea about it.
No, étal connected proposition. No, étal connected proposition. It cannot work with any étal connected type.
Okay.
I don't know.
All right. Thank you again.